Hi, Andy. In the last class, we discussed vibrational spectroscopy. We considered both simple harmonic motion and enharmonic motion also. Now, before going to Raman spectroscopy, a small concept from vibrational spectroscopy, that is Fermi resonance. What is Fermi resonance? What is the concept of Fermi resonance? Okay, that I will explain by an example. For example, if you take CO2, okay, for CO2 fundamental vibration. Fundamental vibration. We discussed fundamental vibration means 0 to 1, that is called fundamental vibration. And overtone, first overtone means 0 to 2. Fundamental vibration is observed at 1330 centimeter inversion, whereas overtone is observed at 1334 centimeter inverse. That means almost those two have same vibrational frequency. Those two have same vibrational frequency. As those two have same vibrational frequency, the interaction may occurs. The coupling of the two signals may take place. Interaction between these two signals may occur, or coupling between these two signals may occur. Because of that coupling, okay, this type of degeneracy is called accidental degeneracy. This type of degeneracy is called accidental degeneracy. Because of that, because of coupling, so generally the intensity of overtone is very low, but because of this accidental degeneracy, the intensity of overtone increases. The intensity of overtone increases. Such phenomena is called as Fermi resonance. So Fermi resonance is simply whenever two spectral lines vibrational frequency matches, then some interaction occurs. Because of that interaction, generally the signal whose intensity is very low, its intensity may increases. That is called as Fermi resonance. Okay. Next one, I am going to Raman spectroscopy. Since in TSGENCO just we may expect 2 to 4 questions only from these spectra, so no need to study in detail and in depth. Okay, mostly we may expect 2 to 4 questions only from this spectroscopy, and again we have organic spectra also. From that also we can get some questions. Okay. Raman spectra. So if you see microwave spectra or IR spectra, in microwave spectra or IR spectra, okay, we recorded spectrum for which radiation? We recorded spectrum for absorbed radiation. Okay, during transitions, rotational transitions or vibrational transitions, how much energy is absorbed? For that we take the signal. Okay, so in microwave IR spectroscopy we concentrate on absorbed radiation, whereas in Raman spectra we concentrate on scattered radiation. We concentrate on what? Scattered radiation. Now, when a molecule is said to be microwave active, it has to possess what? Permanent dipole moment. When IR active, during vibration, the dipole moment of the molecule has to be changed. Similarly, when a molecule is said to be Raman active, what is the condition? Polarizability of the molecule has to be changed. Polarizability of the molecule has to be changed. Polarizability of the molecule has to be changed. Whenever we are applying light energy, okay, generally we apply here laser beam, intense laser beam. Okay, so whenever we are applying that intense laser beam having monochromatic radiation, the polarizability of the molecule has to be changed, or induced dipole has to be created in the molecule. Electron cloud has to be disturbed. Electron cloud is disturbed, charge separation has to be occur, or some induced dipole has to be created, then such molecule is said to be Raman active. So we discussed homonuclear diatomic molecules. This question given in various competitive exams. Homonuclear diatomic molecules are both IR inactive as well as microwave inactive. So their bond. So the information corresponding homonuclear diatomic molecules we cannot get by either microwave spectroscopy or IR spectroscopy, but they are Raman activant. So some induced dipole is created even in homonuclear diatomic molecules. So therefore the information regarding homonuclear diatomic molecules we can get by using Raman spectroscopy. Okay, so you remember this point. Homonuclear diatomic molecules are both IR and microwave inactive, but they are Raman activant. They show Raman spectroscopy. Whenever we are applying laser light, okay, some induced dipole is created even in homonuclear diatomic molecules. Now, what is the principle involved in the Raman spectroscopy? That we can explain by two theories. One is quantum theory, another one is classical theory. Okay. What is the principle involved in the Raman spectra? That we can explain by using quantum theory and classical theory. First of all, quantum theory. Okay. Let us consider E is the energy of the molecule. E is the energy of the molecule before scattering or before interaction with radiation. Before scattering of radiation, initial energy of the molecule is En. And E dash, let us consider energy of the molecule after scattering. E dash is the energy of the molecule after scattering of radiation. Let nu is the incident radiation frequency. Let nu is the incident radiation frequency, and nu dash is scattered radiation frequency. Okay, here I am taking some terms. E is the energy of the molecule before scattering, E dash after scattering, nu incident radiation frequency, and nu dash scattered radiation frequency. Okay. Now we know, according to law of conservation of energy, energy before the scattering, total energy before scattering and total energy after scattering should be same. So initially energy is E plus frequency we are taking nu, that means energy h nu. E plus h nu is equal to, after scattering, the energy of the molecule is E dash, scattered radiation frequency is nu, that means h nu dash. According to law of conservation of energy, so E plus h nu should be equal to E dash plus h nu dash, like this we are taking it. Okay. Now, for example, if the interaction or collision between radiation and the molecule, if the collision between incident radiation and the molecule is elastic scattering, the collision between molecule and incident radiation, that is elastic scattering. Elastic scattering means during collision, is there any exchange of energy or no exchange of energy? No exchange of energy. Energy is not exchanged. That means energy of the molecule before and after collision is same. That means incident radiation frequency and scattered radiation frequency both are same. Incident radiation frequency, scattered radiation frequency same, since no exchange of energy during that collision. That is called what? Elastic scattering. Such scattering is called as Rayleigh scattering. Such scattering is called as Rayleigh scattering. Rayleigh scattering is nothing but elastic scattering, no exchange of energy. Energy before collision and after collision same, or incident radiation frequency is equal to scattered radiation frequency. The collision is inelastic and its energy exchanged. If energy is exchanged, so molecule is giving energy to radiation or molecule is absorbing energy from radiation. Okay, that means energy of the molecule may increases or decreases, or scattered radiation, okay, frequency may increases or decreases. Such scattering is called as inelastic scattering. That means E is not equal to E dash, or nu is not equal to nu dash. That is also said to be Raman scattering. Raman scattering or Raman effect. That is also said to be Raman scattering or Raman effect. This Raman effect was discovered in what? 1928, February 28. Okay. For this, Raman awarded with Nobel Prize, and every year we are celebrating National Science Day to commemorate the discovery of Raman effect or Raman scattering, or that is also said to be Raman shifted. That is also said to be Raman shift. But only some fraction of molecules undergo Raman scattering. Very small number of radiations can undergo Raman effect. That's why to increase the probability we are using intense laser beam. Laser beam intensity is high, more number of photons are present. That's why we are using intense laser beam to record Raman effect. Okay. So Raman effect means what? If the scattered radiation frequency is different from incident radiation frequency, or energy of the molecule before and after collision is not same, that is called Raman effect or Raman shift. Whatever the change in the frequency observed, okay, that is called Raman shifted. Raman shift. Okay. Now, for example, the scattered radiation energy is greater than, energy of the molecule after scattering is more compared to incident energy. Energy of the molecule is increased. Energy of the molecule is increased means scattered radiation frequency decreases. Some energy is given to molecule and molecule energy is increased. That means scattered radiation frequency decreases. And that means then nu dash is less than nu. Scattered radiation frequency is less than incident radiation frequency. Okay. Such lines are called as Stokes lines. The corresponding lines are called as Stokes lines. In Raman effect, again we may get two types of lines, Stokes lines and anti-Stokes lines. If scattered radiation frequency is less than incident radiation frequency, the corresponding lines are called Stokes lines. Now, if E dash is less than E, energy of the molecule decreased. Energy of the molecule decreased means energy is given from the molecule. Energy is given from the molecule. That means scattered radiation frequency increases more compared to incident radiation frequency. Such lines are called as anti-Stokes lines. Anti-Stokes lines. Okay, I will explain it. Anti-Stokes lines. For example, where some vibrational energy levels I am taking 0, 1, and this is some virtual state, intermediate state, some imaginary state we are taking, virtual state. Initially, the energy of the molecule is E, and before scattering, energy of the molecule is E. Okay. Next, we are applying incident radiation whose frequency is nu. We are applying incident radiation whose frequency is nu. Now, scattered radiation frequency is nu dash. Now, nu and nu dash are same or not? Same. So, E and E dash are also same. Okay. After scattering, energy of the molecule is again E dash only. So, this type of scattering is called as what? Rayleigh scattering. Rayleigh scattering. This is the incident radiation frequency. This is the scattered radiation frequency. Okay. The molecule goes to some virtual state, some imaginary state, intermediate state, again returns to same level. So that is called Rayleigh scattering. For example, the transition is occurring like this. This is initial energy of the molecule. This is the incident radiation frequency. Incident radiation frequency. Now, this is the scattered radiation frequency. During scattering, molecule returns to this state and E dash state. Okay, now what about E dash and E dash is greater than E. Now, if you observe, this is the scattered radiation frequency. So, nu dash is greater than nu or less than nu. Nu dash, this gap is less. That means frequency decreases. Nu dash is less than nu. Energy of the molecule is increasing. That indicates that scattered radiation frequency decreases. This type of scattering is called as Raman scattering. In that, the corresponding lines are called as Stokes lines. The corresponding lines are called Stokes lines. Whatever the lines we will get because of this difference in the energy, difference in the frequency, that is called Stokes lines. For example, initially molecule is in this state and V is equal to 1 state. Initially molecule is in the V is equal to 1 state, higher vibrational energy level. This is the incident radiation frequency. This is the incident radiation frequency. It goes to some imaginary state, some virtual state, intermediate state. Now it returns to V is equal to 0 state, and this is the final energy. This is the final energy of the molecule. So scattered radiation frequency is what? Nu dash. Now E dash is less than E. Energy of the molecule is decreased. Energy of the molecule is decreased, but what about scattered radiation frequency increased? Scattered radiation frequency is increased. What about the difference we are getting? That difference is called Raman shifted. Raman shift. Okay, the corresponding lines are called as anti-Stokes lines. So like this we will get Stokes lines and anti-Stokes lines. And these two comes under what? Raman shift. Now what about the intensity of Stokes lines and anti-Stokes lines? If you see, generally Stokes lines are observed whenever, okay, the transitions occur from lower energy level. But here the transitions are occurring from higher energy level. So generally the population present in the lower energy level is high compared to higher energy level. So the probability for anti-Stokes lines is small compared to Stokes lines. So generally the intensity, if you compare intensity of Stokes lines is more compared to anti-Stokes lines. Generally the intensity of Stokes lines is more compared to anti-Stokes lines. Stokes lines are observed, initiated, okay, from lower vibrational energy level, whereas anti-Stokes lines, okay, the corresponding transitions are initiated from higher vibrational energy level. Okay, higher vibrational energy level population is less compared to lower vibrational energy level. That's why its intensity is more compared to its intensity. So this is said to be what? Quantum theory of radiation, Raman scattering. Quantum theory of Raman scattering. So you remember what are Stokes lines, what are anti-Stokes lines, and what about the intensity of Stokes and anti-Stokes lines, that one. And condition and polarizability of the molecule has to be changed during rotation or vibration. We have rotational Raman spectra, vibrational Raman spectra. The transitions are occurring between rotational energy levels, that is called rotational Raman spectra. The transitions are occurring between vibrational energy levels, that is to be vibrational Raman spectra. Okay. Next, second theory is classical theory. Second theory is classical theory. According to this theory, whenever we are taking sample molecules in the presence of electric field, okay, we know electromagnetic radiation possesses both electric field and magnetic field. Electromagnetic radiation possesses both electric field and magnetic field. So whenever we are taking molecules in the presence of electric field, okay, here we have nucleus and electron. Nucleus possesses which charge? Positive charge. Whereas electron possesses negative charge. So nucleus may be attracted towards negative pole of electric field, whereas electron possesses negative charge, so it may be attracted towards positive pole of electric field. So overall what happens is some distortion of electron cloud takes place, or some dipole is set up in the molecule. That dipole is called as induced dipole. So some induced dipole is set up in the molecule because of this interaction. Nucleus possesses positive charge that may be attracted to negative pole. Electron possesses negative charge that may be attracted to positive pole. Because of that, some charge separation takes place. Some induced dipole is created in the molecule. Okay, so if induced dipole is created in the molecule, then such molecule is said to be polarized. Then such molecule is said to be polarized, and such phenomena is called as polarization. Okay. And this extent of polarization or magnitude of polarization depends on two factors. Extent of polarization depends on two factors. One is strength of electric field we are applying. That is depends on strength of electric field. Second one is polarizability of the molecule. Polarizability of the molecule. Strength of electric field E and polarizability of the molecule alpha. Polarizability means the tendency of the molecule to be distorted, the tendency of electron cloud to be distorted, or the tendency of the molecule to set up dipole, that is called polarizability. That is different for different molecules. Same electric field we are applying, and same electric field we are applying to different molecules. In one molecule, more dipole may be created. In another molecule, less dipole, less charge separation may be observed, less distortion may be observed. In another molecule, more distortion may be observed. That is called what? Polarizability. It is a characteristic of given molecule. Depends on the nature of molecule. The ease with which the molecule gets a dipole, that is called polarizability. Okay. So if the polarizability of the molecule changes, then such a molecule is said to be Raman active according to classical theory. If dipole is created, then such molecule is said to be Raman active. So homonuclear diatomic molecules also, some induced dipole may be created. They may not possess permanent dipole moment, but whenever they are taken in the presence of electric field, some induced dipole may be created. So they are said to be Raman active. And this point you may remember previously given in some competitive exams. That is spherical top molecules. Spherical top molecules, particularly if you consider rotational motion. If you consider rotational motion, okay, as their spherical symmetry, as they have spherical symmetry, so if you consider rotational motion and rotational Raman spectra, if you take spherical top molecules, if you take rotational Raman spectra, I told you we have rotational Raman spectra, vibrational Raman spectra. Whenever we are applying laser light, the transitions occur between rotational energy levels, that is called rotational Raman spectra. The transitions occurs between vibrational energy levels, that is to be vibrational Raman spectra. Okay, here they have spherically symmetric shape. So whenever the electron cloud is distorted, even they possess spherically symmetry only. That's why they are rotational Raman inactive. Spherical top molecules are rotational Raman inactive. Okay. Which molecules are examples for rotational Raman inactive? Spherical top molecules like tetrahedral, the molecule belongs to tetrahedral point group, octahedral point group. CH4, CCl4, SF4, SF6, UF6, etc. Okay. Next one. The extent of polarization. Polarization is given by alpha into E, and if you apply more electric field for a given molecule, alpha is constant. If you apply more electric field, more induced dipole is created, and mu means here induced dipole. Next, for a given electric field, if you take different molecules, and alpha may be different for different molecules, since extent of polarization, induced dipole moment may be different for different molecules. For a given electric field, alpha may be different for different molecules. So extent of polarization, polarizability of the molecule is given by mu by E, and mu indicates induced dipole created in the molecule, and E is the strength of electric field we are applying. Okay, so this is the expression for alpha. Generally, polarizability is high for more polar bonds or less polar bonds. You see, polarizability is high for less polar bonds. The distortion in the electron cloud is high for less polar bonds. Less polar bonds are highly distorted. So you remember, so polarizability, intensity of the spectral lines, is high for less polar bonds. Intensity of the spectral lines is high for less polar bonds. Next one, if you see polarizability, whether isotropic or anisotropic. Polarizability is whether isotropic or anisotropic. If you measure a property in different directions, if you get different value, then it is said to be anisotropic. In all the directions, if you get same value, then it is said to be what? Isotropic. If you measure a property in different directions, if you get different value, that is said to be anisotropic. If in all the directions you are getting same value, that is said to be isotropic. So whether polarizability is anisotropic or isotropic. For that, okay, for that I am explaining by this example. Okay, here electric field I am applying along the bond axis and along the bond axis electric field, and electric field I am applying across the bond axis. H2 molecule we are taking homonuclear diatomic molecule. Okay, we are applying electric field along the bond axis and across the bond axis. Then what happens if you see here more dipoles are created. That means here polarizability is higher. It is observed that here polarizability is high, relatively high, whereas here polarizability is relatively small. So it indicates that polarizability depends on direction. Polarizability depends on direction. So polarizability is said to be what? Isotropic or anisotropic? Polarizability is said to be anisotropic. Polarizability is said to be anisotropic. And polarizability has the dimension of volume. Polarizability has the dimension of volume. More distortion means more change in the volume. Small distortion means small change in the volume. So if more change in the volume is observed, then that molecule is said to be more polarized. Small distortion means small change in the volume is observed, then such molecule is said to be less polarizable. Okay, more distortion or more change in the volume means more intensity oriented. Small change in the volume, small distortion means less intense spectral line implicated. Okay, so polarizability has the dimension of volume. Next, polarizability is isotropic or anisotropic. Anisotropic since in different directions, if you apply electric field, different value we are getting, same molecule we are taking, but extent of polarization is different. Here, along the molecule, extent of polarization is high. Across the molecule, if you apply, extent of polarization is small. So that is said to be anisotropic. Okay. The next one, this is important. Rule of mutual exclusion. So I am concentrating only on some important areas of the rule of mutual exclusion or complementary nature of IR and Raman. Complementary nature of IR and Raman spectra. Rule of mutual exclusion or complementary nature of IR and Raman spectra. So based on this, if you compare both IR and Raman spectra, for a given molecule, by comparing that we can get shape of the molecule or geometry of the molecule, whether it possesses linear structure or non-linear structure, whether it is centrosymmetric or non-centrosymmetric. Such information we can get by comparing IR and Raman spectra for a given molecule. According to rule of mutual exclusion, if you take a centrosymmetric molecule, whatever the vibrations, those are IR active, okay, those are Raman inactive. If a molecule possesses center of inversion, IR active vibrations are said to be Raman inactive, whereas IR inactive vibrations are said to be Raman active. IR active vibrations are Raman inactive, IR inactive vibrations are said to be Raman active. That is called rule of mutual exclusion. Okay, like that it is observed for centrosymmetric molecules or the molecules having center of inversion. That means whether centrosymmetric molecules possess any common lines in IR and Raman or no common lines. If you see, no common lines in IR and Raman. So from this, if you record IR and Raman spectra for a given molecule, we have to compare IR and Raman spectra. If any common lines are present, that is non-centrosymmetric molecule. If no common lines, that is said to be centrosymmetric molecule. Okay? If common lines are present and if if some of the vibrations are both IR active and Raman active, or if some of the vibrations are both IR inactive and Raman inactive, some common lines are present, then such molecule is said to be centrosymmetric molecule or non-centrosymmetric molecule. Non-centrosymmetric molecule. Non-centrosymmetric molecule. And already I told you, from IR spectroscopy, if Q branch lines are absent, Q branch lines are absent, then that is said to be what? Linear molecule. So based on that, we can verify whether it is a linear molecule or non-linear molecule. If Q branch lines are absent, that is linear molecule. Next, if common lines are present, that is linear non-centrosymmetric molecule. If no common lines, that is said to be linear centrosymmetric molecule. If Q branch lines are present, that is said to be non-linear molecule. If Q branch lines are present, that is said to be what? Non-linear molecule. So like this, we can give shape or geometry of the molecule by using this principle. This is called rule of mutual exclusion or complementary nature of IR and Raman. For example, if you take CO2, CO2, IR and Raman, we know symmetric stretching vibration, next anti-symmetric stretching vibration, next we have bending vibrations. Bending vibrations are degenerate, both occur at same frequency. Bending two stretching vibrations, we have two bending vibrations for CO2. It is, which type of molecule it is? Centrosymmetric molecule. Centrosymmetric linear molecule we have. CO2 is centrosymmetric linear molecule. Center of inversion is present. Okay. So we know symmetric stretching is IR inactive or active. IR inactive. Asymmetric stretching active. Bending vibrations also IR active. Since here dipole moment, no change in the dipole moment. In symmetric stretching, dipole moment of the molecule is not changed. Okay, in symmetric stretching, dipole moment of the molecule is not changed, so that is IR inactive. In these two, dipole moment of the molecule changes, so they are active. Okay, Raman. So as it is centrosymmetric molecule, IR inactive is said to be what? Raman active. IR active is said to be what? Raman inactive. So anti-symmetric stretching vibration is IR, Raman inactive. Bending vibrations also Raman inactive. Bending vibrations also Raman inactive. Okay. If you see the lines also, we'll get lines like this. Various branch lines, if you see, this is inactive, no need to consider. Here we'll get parallel vibration. Stretching vibration is what? Parallel vibration. The oscillating dipole is along the bonding axis, so that is considered parallel vibration. Bending vibration, oscillating dipole is perpendicular to the molecular axis. So here we discussed selection rules are delta J is equal to plus or minus 1. Here delta J is equal to what? 0, plus or minus 1. So here P branch lines and R branch lines will get here. P, Q, R branch lines will get. So absence of Q branch line here indicates it is a linear molecule. Absence of Q branch line here indicates it is a linear molecule, and no common lines in the IR and Raman, that indicates it is a centrosymmetric molecule. So overall what we will get? Linear centrosymmetric molecule. Overall we will get linear centrosymmetric molecule. For example, if you see for N2O1, similarly if you see for N2O, what about the nature of N2O, whether it is linear molecule or non-linear molecule, whether it is centrosymmetric molecule or non-centrosymmetric molecule? N2O, this data may be given to you. New bar value 589, 1285, 2224, IR active, PQR given, active, PR, active, PR. Raman. Inactive given, inactive, active, inactive, active, active given. Inactive, active, active. So like this, the data given here, common lines are there or not? Yes, these two are observed in IR as well as Raman. These two are observed in IR as well as Raman. So therefore, some common lines are present. Some common lines are present means whether it is said to be centrosymmetric molecule or non-centrosymmetric molecule. Non-centrosymmetric molecule, center of inversion is absent in N2O. Next, whether it is linear molecule or non-linear molecule. Here and here, if you observe, Q branch line is absent. Here and here, Q branch line is absent. So that indicates that it is a linear molecule. So overall, N2O is what? Linear non-centrosymmetric molecule. N2O is linear centrosymmetric molecule. This is the structure of N2O. This is the structure of N2O. Okay. So it is an example for what? Non-linear, linear non-centrosymmetric molecule or non-centrosymmetric linear molecule. How we confirm linear? Absence of Q branch lines. How we confirmed center of inversion present or absent? Common lines are present. If common lines are present, that is non-centrosymmetric molecule. And finally, one more example I am giving. Okay, Q branch line present means this corresponds to what? Bending vibration. This corresponds to bending vibration. These two are stretching vibrations. I told you generally for anti-symmetric stretching vibration, the vibration frequency is high compared to symmetric stretching vibration. This is symmetric stretching vibration. So this corresponds to bending vibration, symmetric stretching vibration. This is anti-symmetric stretching vibration. So I told you vibrational frequency generally for bending vibration is small compared to stretching vibrations. Similarly, I am giving one more example, SO2 vibrational frequency, IR and Raman. Here given 519, 1151, 1361. So this corresponds to what? Bending vibration. This corresponds to symmetric stretching. This corresponds to anti-symmetric stretching vibration. Active, it is given PQR. Active, PQR. Active, PQR. Active given. So here, now common lines are present or not? Yes, common lines are present. That means it is non-centrosymmetric molecule. Okay, non-centrosymmetric molecule. SO2 possesses center of inversion or it doesn't possess it? It doesn't possess center of inversion. Now whether Q branch lines are absent or present? Q branch lines are present. That means it indicates it is a non-linear molecule. What is the structure of SO2? This is the structure of SO2. It is a non-linear molecule, and whether center of inversion is present or absent? Center of inversion is absent. So it is an example for non-linear non-centrosymmetric molecule. Non-linear non-centrosymmetric molecule. Okay, generally whose vibrational frequency is small, that corresponds to bending vibration. After that, symmetric stretching. After that, anti-symmetric stretching. Okay, this is about Raman spectroscopy, some important concepts from Raman spectroscopy. So you remember those points. And homonuclear diatomic molecules. Homonuclear diatomic molecules, both IR inactive and microwave inactive, but they are Raman active. Okay, which are rotational Raman inactive and spherical top molecules are rotational Raman inactive. Okay, such type of questions they are giving, and which of the following is rotational Raman inactive? In that, one of them may be given spherical top molecule. Okay, belongs to tetrahedral and octahedral point. Next, quantum theory. According to quantum theory, Raman shift, when we may get Raman shift, and if the energy of the molecule before and after scattering is different, then we may get Raman scattering, or incident radiation frequency and scattered radiation frequency are different. When we get Stokes lines, and if scattered radiation frequency, okay, and when we are getting Stokes lines, and if energy of the molecule is more compared to incident radiation, if energy of the molecule after scattering is more compared to incident radiation energy, or scattered radiation frequency is less than incident radiation frequency, then we'll get Stokes lines. If E dash is less than E or nu dash is greater than nu, then that corresponds to what? Anti-Stokes lines. And generally intensity of anti-Stokes lines is less than Stokes lines. And rule of mutual exclusion. If IR and Raman possess some common lines, that is said to be non-centrosymmetric molecule, no common lines, centrosymmetric molecules, and absence of Q branch lines in IR spectra indicates it is linear molecule. If Q branch lines are present in all the IR lines, IR signals, if Q branch lines are present, that indicates it is a non-linear molecule. Okay, right? This is about Raman spectra. Thank you. In the next class, we will discuss NMR spectra.